Hi, good morning everyone. So this is joint work with Dalu here. So I'll talk about an old problem which was kind of famous during its time, but then it got settled, and so we now kind of have a simpler proof for it using a technique that was developed by Pavel and Jing Huang. Okay. So let's define all these terms. Okay, so so this topic was started by Quatel and Hammer in 1977. So they were asking about. So they were motivated by applications from linear programming and a lot of different areas. So this topic seemed to have come up in a lot of different areas simultaneously at around this time, 1977. So the question they asked is the following: suppose you have a graph G and it has n vertices. Okay. So now if you think of a subset of vertices of your graph, you can think of the characteristic vector of that subset, right? So it is basically a vector of n bits, one bit corresponding to each vertex of your graph, and you have a 1 in only those positions which correspond to vertices that are in your set, right? So for a given set S, it corresponds to a vector 0, 1, bit string, right? N bits. So these vectors, these 0, 1 vectors, so if you look at this space, right, the set of all 0, 1 vectors, n bit vectors, they are the corners of an n-dimensional hypercube, right? An n-dimensional hypercube with one corner, in the all positive quadrant, right? So Quatel and Hammer was interested in this question. This is somehow motivated by some linear programming and all. So suppose that you have this n-dimensional space in which this hypercube is sitting, and you want an n-dimensional, you want a hyperplane, right? So if you have a hyperplane in an one-dimensional hyperplane in this space, it will partition this space into two half spaces, right? That's what it is. So suppose that you want to find the minimum number of half spaces, right? So I said if you look at the intersection of these half spaces, that will contain some corners of your hypercube, and those corners will be exactly the sets corresponding to the independent sets of your graph G. Okay. So how many half spaces do you need? This was Quatel and Hammer's question. Okay. So basically, if you just write it algebraically, the question is, what is the minimum number of such linear inequalities? Right. So each of these is a linear inequality. You can see that they are on n variables, x1 to xn. Right. Each variable corresponds to a vertex of your graph, and each variable takes only values 0 and 1. Okay. So what you want the set of linear inequalities to satisfy now is that if you plug in the characteristic vector x1 to xn of an independent set in your graph, then all the linear inequalities need to be satisfied. All of them have to be satisfied, right? And if it is not the characteristic vector of an independent set, then some linear inequality should be violated, right? So the solutions, the 0, 1 solutions of the set of linear inequalities are exactly the independent sets of the graph G, right? So yeah, why should such inequalities exist and all these things we'll see. So so the minimum number of such inequalities is exactly the parameter that Quatel and Hammer were looking for. So they called it the threshold dimension of a graph, right? So these are the thresholds. Okay. So it is the minimum number of inequalities such that the characteristic vectors of only independent sets satisfy all of them. So in a sense, if I look at just one edge, right, a set which contains two elements which are adjacent, then that means that if I put ones in those places and zeros in every other place, at least one of the inequalities have to be satisfied, be violated. One of the inequalities have to be violated, right? So so study this. They studied those graphs for which one linear inequality will suffice, right? So those graphs for which you can write a single linear inequality of this form. Okay, so this is a threshold, and these are reals, such that the inequality is satisfied only when you put in the characteristic vectors of the independent sets in your graph, right? So what are those graphs for which only one inequality is required? So they are exactly the threshold graphs. So they have threshold dimension 1, right? They need only one linear inequality. And the structure of threshold graphs was studied a lot, and it's a quite very structured class, right? So they are split graphs. They are a special kind of interval graphs, right? They are the interval graphs in which you have a lot of point intervals, and all the big intervals start from one endpoint. Okay, they are exactly that class. Then they are also co-graphs, the subset of co-graphs, and they are just exactly the graphs which do not contain an induced 2k2, p4 or c4. So this is the exact. So there are many equivalent definitions of threshold graphs. So this will be the most useful, for our purposes. You can just think of threshold graphs as those graphs which don't have an induced 2k2, a p4 or a c4. Okay. So now if you go back here, suppose that your graph has, so your graph is some graph, it's not a threshold graph, but let us say that there are k linear inequalities which satisfy the required property, right? Yeah.
So what are those coefficients? Like, do you just want any hyperplanes or?
So this defines a hyperplane. Right? So,
no. So do you have some restrictions on what kind of hyperplanes or just any hyperplanes? Like those coefficients and the coefficients.
Oh, coefficients. Okay. So the coefficients are just reals. This coefficients and this threshold are just reals. These variables. Yeah.
Is there a trivial number of?
Yeah. So that comes from what we are going to say now. So if you just observe this, the first thing that will strike you is that if I just take out this linear inequality, right, that corresponds to a threshold graph, right? So what if I take out this linear inequality? So the one linear inequality describes a graph. How does a linear inequality describe a graph? So is it obvious to you that if I give you one linear inequality, you can immediately construct the graph corresponding to that linear inequality? Because you take any pair of vertices to decide if they are adjacent or not, you just use this equation, right? So if you have just one linear inequality, can't you construct the graph which is described by the linear inequality? You take any pair of vertices, you put them into this inequality. If it's violated, there's an edge. If it's not violated, there's no edge, right? So once you have a linear inequality, it completely describes a threshold graph for you, right? So now let us say that your graph has so many inequalities which will satisfy the requirement. Now let me write the threshold graphs corresponding to each inequality by the side, right? So what you can say is that every independent set of your original graph will also be an independent set in each of these threshold graphs that I have written, right? Because they also satisfy that inequality, right? And if there is an edge between some vertices, right, it may not be an edge in this threshold graph because it may not violate this linear inequality, but it is going to be violated in some linear inequality and it will be an edge in that threshold graph. Right? So basically what you're saying is that the threshold dimension is basically just the minimum number of threshold graphs with which you can cover the edges of your graph. Right? Now it has become completely graph theoretic, right? So basically the threshold dimension turns out to be the minimum integer. So this Tg denotes the threshold dimension. It is a minimum integer such that G has a threshold cover of size k.
So in that sense, T1, T2, everything will be 1.
No, these can be some real numbers. So T1, T2. So these are so suppose you have a collection of linear inequalities, and this satisfies the property that if I put in an independent set of G into this x1 to xn, all of them are satisfied.
For the other those k equation you allow
any t. So that t can be any real number. Oh, it is the minimum number of equations. Yeah. So this basically it is the minimum number of half spaces, right? So basically it is a minimum number of So k has to be minimized here, right? So the threshold dimension of your graph is the minimum number of linear inequalities that you need to write, so that only independent sets satisfy all the inequalities, right? So what we just said was that since every inequality corresponds to a threshold graph, which will be a subgraph of your graph, you can take these threshold graphs which correspond to each linear inequality will form a cover of your graph, right? Similarly, if you have a cover of your graph using some k threshold graphs, you just write down the linear inequalities corresponding to each of your threshold graphs, right? And that will give you a set of equations, right? So basically, this threshold dimension happens to be exactly the smallest number k, such that you can cover the edges of G using k threshold graphs. So now that answers your question if it's bounded, because if you just take one single edge and put all isolated vertices, that is a threshold graph. So the number of edges is an upper bound on the threshold dimension of any graph. Okay. So okay. So if we just look at threshold graphs, one easy way to define threshold graphs is the following way. Suppose that you have two edges AB and CD, okay, and there are two parallel missing edges between them. Okay, so I don't say anything about these two. They could be edges or non-edges. I don't know. Okay, but if you have this structure in your graph, then it cannot be a threshold graph, right? Because of the simple reason that then you have either a 2K2 or a P4 or a C4 in your graph, right? So threshold graphs are exactly those graphs which don't contain any of these. So if you don't have both these edges, then this is a 2K2, induced 2K2 in your graph. Two edges which don't have any edges between them, right? And if you have just one edge between them, then it will be an induced P4, a path on 4 vertices. If you have two edges between them, it will be an induced C4, right? So basically, threshold graphs are exactly those edges which don't have crossing, exactly those graphs which don't have a pair of crossing edges, right? So that's the same thing, right? Okay. So now this motivates Quatel and Hammer to formulate the auxiliary graph G prime, okay, of G. Okay. So what is G prime? The vertex set of G prime is the edge set of G. Okay. So basically you want to capture the conflicts between edges, right? So now you draw a graph in which there's a vertex for each edge of G, and whenever these two edges are crossing, in your graph you put an edge between those vertices in G prime, right? So this is clear, right? If you have a threshold cover of size k, right? If your graph can be covered with k threshold graphs, then you take just one threshold graph, right? Inside, if you take the edges corresponding to one threshold graph, and you can
cannot have two crossing edges.
Yeah, you cannot have two crossing edges, right? So basically we are talking about the chromatic number of G prime, right? So we are saying that if you have if you can cover your graph with k threshold graphs, then you can color the vertices of your auxiliary graph with just k colors, because you take each of your threshold graph, whatever edges are there in that thing, you color the auxiliary graph with the first color. Now you take your second threshold graph, whatever edges are there, you color it with this thing. Okay. So basically, what you're getting is not a coloring, but a partition of your G dash, but a covering of your G dash with so many independent sets. But then there will also be a coloring, right? So this is clear, right? So they ask this question: is it always equal? So is it sufficient? So if you want to find the threshold dimension of a graph G, is it sufficient to just construct this auxiliary graph and somehow find its chromatic number? Will these parameters be equal, right? But so this was open for some time. Then in 1984, so this was asked in 1977. So in 84, Cousins and Leibowitz constructed graphs, okay, showing that this is not true. Okay, so for every k that is 4 or more, so 4, 5, 6 or whatever number you choose, they can give you a graph whose auxiliary graph will have only chromatic number k. Okay? But you won't be able to cover the edges of your graph with k threshold graphs. You will need more. Okay? So this conjecture is not true in general. But you have to note that this is only for k greater than or equal to 4. So what about k equal to 2? So that is what this talk is about. Okay, the k equal to 3 case is still open. It's unknown. Okay. So we'll focus on the k equal to 2 case now. Okay. When does a graph have a threshold cover of size 2? Okay. Okay, so just a bit of history. So threshold graphs can be recognized in linear time. So we have to. So this seems to have been an intensely studied topic at one point. So there is even a book written by Mathew and Pellet on threshold graphs, in which they compile all the known results about threshold graphs. So they can be recognized in linear time, and then Quadal and Hammer in their original work showed that computing the threshold dimension is NP complete. Okay. And then in 81, Ibaraki and Pellet conjectured that the question of the conjecture of Quadal and Hammer is actually true if G prime is bipartite, right? So for the k equal to 2 case, Ibaraki and Pellet conjectured that it is true, but then you have to notice that Cousins and Leibowitz came later and they said that they don't believe this conjecture, but it turned out to be true. So Ibaraki and Pellet, they have a very involved proof, goes through several stages of reductions, and it is kind of very complicated. And they managed to show that if in some special cases this is actually true. Okay, what are the special cases? That if G is a split graph, then it's true. So that itself has resulted in a lot of other results in other areas, because in many other areas it's only split graphs that they are interested in. And also if G prime contains only 2 non-trivial components, then still they can show it. But the proof is still complicated. And see, you have to note that if this conjecture is true, right, then that immediately implies a polynomial time algorithm to decide if a graph can be covered with 2 threshold graphs, right? You just construct the auxiliary graph and check if it's bipartite. That's it. Right? So Yanakakis narrowed the gap. Okay, so this was still open at that time. Yanakakis showed that if you want to decide even if so this is a celebrated paper of Yanakakis from which a lot of problems turned out to be NP complete. So he showed that even if you just want to check if a graph can be covered with 3 threshold graphs, that itself is NP complete. Okay. So only the case 2 remained to be checked, whether if it was polynomial time or NP complete. And then came Rashley and Simon. So this is their stock 95 paper. So they proved Ibaraki and Pellet's conjecture. They showed that if the auxiliary graph is bipartite, then your graph can be covered with 2 threshold graphs. Okay. So the problem of checking this is polynomial time solvable. But the proof is long and not easy. So in the textbook of Mahadev and Pellet, the proof of this theorem takes up about 22 pages. So just the proof. So it is, they even extend the methods of Ibaraki and Pellet, and it is quite a lot of work. So what we propose today is that there is a much simpler proof, very direct proof based on some technique that was introduced by Pavel and Jing Huang, also in 1995. Okay, but for some other problem. So first we have to understand what is hard in this, right? So why is it hard to prove this conjecture that if your auxiliary graph is bipartite, then can't you just produce a 2 coloring of your bipartite graph of the G prime, and then those edges, right, which got the color blue. Let's say I'm coloring the auxiliary graph with blue and red, and I take the vertices which are colored blue and they correspond to edges in your graph G, right? Can't I just take those blue edges and won't they form a threshold graph, and can I take the red edges and won't they form a threshold graph? No, it's not so simple. It's even not obvious when so if your graph G prime had only one connected component, right, then there is only one 2 coloring, right? But the problem is that more often than not, you will have your G prime will contain a lot of components, lot of isolated vertices. So you don't know what to do with these edges which are isolated, right? They don't form a crossing pair with any other edge, right? And also you when you have many components, you fix a bicoloring on one component, then you have two possibilities for the bicolorings on the other component, right? So you don't have time to check all colorings, right? Because if there are many components. So this is the thing that makes this problem difficult. Okay. So then Pavel and Jing Huang in 95. This is a JGT paper. They introduced something called the lexicographic method. Okay, and they showed that this is kind of like a simple and technique which can really simplify some complicated proofs which involve generating representations of graphs. Okay, for example, if you look at the class of comparability graphs, they are those graphs. So this is just another class not related to threshold graphs. So comparability graphs are those undirected graphs for whose edges can be transitively oriented. Right? You will be able to orient the edges so that if you have UV and VW, then UW is an edge in the graph and it will be oriented in the direction U to W. Okay? That's a transitive orientation. So so they show that this. So this is a well-known theorem. This comes from work of a lot of people, I think, starting from Gilmore, Hoffman, Newell, Lempel, even, and Golumbik. So there is a full proof of this fact given in Golumbik's textbook. That is also very long and very involved. So what is the auxiliary graph here? Right. So you can see that in this statement also there is an auxiliary graph that wants to be bipartite, right, if the graph is a comparability graph. So again, this auxiliary graph is defined because of the necessities of this transitive orientation. So here the difference is that it is different from the G prime which we saw earlier for threshold graphs, in the sense that the vertices of G star are not the edges, but for every edge there are two vertices, UV and VU. Right? So for every edge you need to choose either this orientation or this orientation. Right? So there are two vertices for every edge, right? And if once you find a bicoloring of your G star, you take out one color class of it, and that color class will contain some pairs U, V, and if you put those orientations on your edge, it will be a transitive orientation. Right? This is what you want to do, right? So then this again, like in our auxiliary graph G prime, we had the edges captured the conflicts, right? There was an edge between two vertices if those two edges could not be put in one threshold graph. So similarly, you have edges here which capture these things. Okay. So what you have to notice that here too, the essential problem here also is that this auxiliary graph G star could be disconnected. It could have many components, and then it's not easy to find out exactly the right bicoloring of this auxiliary graph, because every component has flexibility now, right? And only one coloring, or only some colorings will give you a valid transitive orientation, and the question is how to find this coloring, right? So this is so the known proofs at this time were all very complicated, and finding this coloring involved a lot of steps. But what Pavel and Jing showed was the following. They show that there is a very simple proof for this. It's just two paragraphs, okay, which can show the same thing. So what they do is the following. Okay. So they take an ordering of the vertex set to begin with. Okay, an arbitrary linear ordering of the vertices, and then they compare sets of vertices lexicographically with respect to this ordering. Okay, so what do you mean by lexicographic comparison? So let us say that you have some set S, and this less than is some linear order over the set S. It is some ordering of the elements of S. And let us say that you have two subsets of S which are of the same cardinality. They have T elements each. So let A1, A2 to AT be the elements of A written in the order in which they appear in this linear order less than, and let B1 to BT be the order in which the elements of B be the elements of B written in the order in which they appear in the linear order less than. Okay. Then we say that A is lexicographically smaller than B, denoted by A less than B, if there is some position in which A beats B, right? A has a smaller value than B, and for all lesser positions, all positions to the left, they are equal. This is just the dictionary order, right? So there is one position at which the element of A is smaller than the element of B, and all smaller elements of A and B are both equal. Okay? So this is denoted by A less than B. Okay. So the lexicographic method works as following for comparability graphs. Okay. So this is not for the threshold cover problem. This is for recognizing and orienting comparability graphs. You choose an arbitrary ordering of your vertex set, an arbitrary ordering less than of your vertex set, and now you want to generate a specific bi-coloring of your auxiliary graph G star. Right? This is what we want. Okay? So what we do is that among the uncolored vertices of G star, okay, you choose the lexicographically smallest edge. Okay, so that edge. So if you look at all edges, they are sets of just two elements, right? Out of that, you choose the lexicographically smallest edge, which is not colored yet. Okay. Then you look at that edge. Okay. Now you orient that edge from left to right. Okay. So this corresponds to saying that if U less than V, then you choose the orientation UV. Okay. So by coloring that vertex with blue, it just means that I am choosing that orientation and not the other. Okay. If V is less than U, then you choose this orientation. You color that vertex as blue, and once you color one vertex in a component, that fixes the coloring of the remaining component, right? I mean, that fixes the colors on all the other vertices of that component, right? So you just propagate the coloring and color that component completely. Now you repeat. Now if there is some component with uncolored, vertices, you then, you pick the lexicographically smallest edge that is uncolored now, color it in the following way, propagate the coloring. Just do this, and it so happens that if after the auxiliary graph is completely colored, you just take out the blue vertices, the vertices that go, they will give you some pairs, right, which are the orientations on the edges that you need to put, and that will happen to be a transitive orientation. Right? So this is such a simple algorithm, there's nothing in it. So you would expect that an algorithm so simple would have a very hard correctness proof, right? But no, the proof is just so simple, and it's just so what they do is something very neat. So the proof is just, let's say, one paragraph or two paragraph, but it's clever. So what they so the thing is that if at all there can be a problem in your orientation, that can occur only in the form of a directed triangle, a triangle that forms a cycle, right? So then you have to look at, so suppose that there are many such triangles in your graph, you have to look at the lexicographically smallest triangle. That is the idea. So if you look at the lexicographically smallest triangle, then you can prove using the triangle lemma some stuff that there is a contradiction. It will never happen. So this is the thing. Okay. So we want to use the same method to try to simplify Rashley and Simon's proof for the threshold cover. Right. This is what we are doing. Okay. So we have almost the same ingredients, but there are also some major differences. So recall that now we are in the threshold cover problem. Our problem is to check if a graph, the edges of a graph can be covered with two threshold graphs, right? So it's not a partition of edges now anymore. It is a cover. So some edges could occur in two threshold graphs. But you have to, so if an edge forms a crossing pair with some other edge, then it cannot be in both the threshold graphs, right? Because one has to go in one threshold graph and the other has to go in the other threshold graph. So you cannot put either of them in both, right? You have to just put it in one of the parts, right? So okay. So we want to again, now G prime is our auxiliary graph. We want, and so that it's not pairs now. So every vertex corresponds to an edge, and we want to color the vertices of the auxiliary graph with blue and red. And finally, we want to say that, and some of the vertices of this auxiliary graph, we give it both the colors, blue and red. Okay. So it's not actually a proper, coloring. It's like some vertices will be colored blue. It will be a proper coloring, but so basically what we'll do is that, this auxiliary graph G prime will have some non-trivial components and many isolated vertices. Right? So every non-trivial component will get a proper coloring of red and blue. But the isolated vertices, we consider them to have both the colors red and blue. So this is basically the coloring that we'll generate. And it seems that we cannot start with an arbitrary ordering of the vertex set, like Pavel did, but it's not, we still don't have a counterexample to show that this is actually required. So it is possible that our algorithm will even work with an arbitrary ordering less than, but the proof becomes very simple if you start with a Lex BFS ordering of your vertex set. Okay, so what is a Lex BFS ordering? So we'll come to that in the next slide. So it is a particular ordering of the vertex set which can be generated in linear time. So there is an algorithm called lexicographic breadth-first search by Ross, Tarjan and Luker. So what we do is we start not with an arbitrary ordering, but with the Lex BFS ordering. Then we do almost the same thing, right? We just assign the color blue to the lexicographically smallest vertex, smallest edge, right? And then propagate the color in that component. Then repeat until all vertices are colored, and the remaining vertices will all be isolated vertices, right? Trivial components. You give them both the colors blue and red. Now, what we claim is that if you look at only those edges which got the color blue, they will form a threshold graph. If you look at only those edges which got the color red, they will also form a threshold graph, right? This is what we want to prove. So we'll go to what this Lex BFS is, right? So this Lex BFS was an algorithm that was invented by Ross, Tarjan and Luker, I think. So one of the major uses was in recognizing caudal graphs in linear time. Okay, so there's a linear time partition refinement algorithm for doing this. So basically what this algorithm does is it is a variant of your standard breadth-first search, okay, and it visits vertices in some order. But you can see this in the following way. So there are, at some point, there are some vertices of your graph that have already been visited, right? So now you have to decide which vertex to visit next, right? How do you decide this? This is intuitively something like this. The already visited vertices, you can think of them as exerting some kind of force, okay, on your unvisited vertices, okay? And every vertex has a different strength of force, right? So the vertices that were visited earlier, okay, have a stronger force than vertices that were visited later, right? So the next vertex that you pick in your Lex BFS is always a vertex which experiences the strongest force, okay? So basically the only property that we need is the following. If you have a Lex BFS ordering and A, B and C occur in this ordering in your Lex BFS, and let's say that AC is an edge but AB is not an edge, right? Then why was B chosen after A, right? So A was visited. So think of the step at which A was already visited, and then you somehow chose B, right? But C was available and C was experiencing a force from A, right? So it means that B was chosen because somebody even earlier than A was exerting a force on B, and that was not exerting a force on C, right? So basically there's a vertex X before A in your Lex BFS order, and you have this edge and this edge is not present, right? So this is the standard property of Lex BFS ordering, and this will be helpful for us. So okay, so now we have some time. I'll try to give the proof. So I told you that it's a simple proof, so I'll try to convince you. So let's say that so what I'm saying is that once you do this, the blue edges and the red edges, they both give threshold graphs, right? Suppose not, then either the blue graph is not threshold, which means it has two crossing edges, or the red graph is not a threshold graph, so it has two crossing edges, right? So when I draw like this, it just means that these two are blue edges which got the color blue, okay, and these two are edges which didn't get the color blue, or they are not even edges, right? In either case, you have a problem in your red graph, right? These could be edges in your graph, but they may not have got the color blue, they might have been colored red, right? And the same case here. So basically this breaks down to these cases, right? So you can see that these are both the same case, okay? So basically in my graph, if I have a situation like this, so you have to note that we don't say anything about these two edges. They may be edges or non-edges, we don't know. So if I have a configuration like this in my graph, I should not color it in this way, red, blue, red, blue, right? Because if I do this, then the blue graph contains this. Right? Similarly, if I have a configuration, I shouldn't even color that configuration like this, because then I will have this. And also, if I have a C4, I shouldn't color it in an alternating fashion like this, right? Because if I do this, again, I have this situation in my red graph. Right? So if these had both the colors, then I would have been happy, right? Because then there's a blue, and then this problem is not there, right? So I should never color a configuration that forms, a P4 kind of thing. So these can be edges or non-edges. Okay, I shouldn't color it in this way, or I shouldn't color. I shouldn't produce an alternating C4. Right? This is what I have to ensure. So if we just ensure that the coloring that our algorithm generates will not contain any of these configurations, then we are done. Right? Okay. So we'll call these the type 1 configurations or something. Okay, the almost alternating C4 configuration. One edge is missing. It's missing in the graph. Okay, so now these are in the graph. So this is a missing edge in the graph, and I have colored it like this. Okay, here all the edges were there, and I got. So let us say that this is a type 1 configuration. So I suppose, for the sake of contradiction, that our algorithm produced this kind of a problem. Okay. Okay, so let us call it A, B, C, D. So remember that our algorithm always preferred the color blue over red. Okay, so if you go back to the algorithm, see, whenever I find the lexicographically smallest vertex, I assign the color blue to it, right? And it's during the propagation of the color that the color red gets assigned to other vertices, right? So whenever I choose the lexicographically smallest vertex in uncolored vertex, I always give the color blue. Okay, so blue is my preferred color in that sense, right? So suppose that your coloring algorithm did this bad thing. Okay, it did this. Okay? But notice that this is not the preferred color, right? Why did this edge get the red color? I wouldn't have chosen this as a lexicographically smallest edge at some point, because then if that happened, I would have given it blue, not red. Right? So this means that there is a path. Okay. In the auxiliary graph. So you can see that this is a path in the auxiliary graph, right? So this edge will be adjacent to this edge in the auxiliary graph, because you have this crossing thing. So it is just drawn in the crossing fashion so that the picture looks nice. It's basically the same thing. You can twist these edges and you will get the same thing, right? So so it means that there was a lexicographically smallest edge xy in that component, which I took and I gave the color blue, right? And that propagated the colors along that component, and that made this edge turn red. That is what must have happened, right? So and I know, so let that edge be xy. So I know that this xy is lexicographically smaller than this bc, right? So this was the smallest uncolored vertex in the component of G prime, which also contained this vertex, right? So this xy should have been smaller than bc lexicographically. So you have to note that these vertices all need not be distinct. Right? Maybe this vertex is the same as this vertex. Right? There could be edges here. There could be edges here. We don't make any claims. All these vertices need not be distinct. Okay? We don't make any such assumptions. Only that when we draw a non-edge, it will be a non-edge, and when we draw an edge, there will be an edge. That's the only thing that we assume. Okay. So so now the first thing that we can notice is that this has to be an edge. Why is that? Because if this was a missing edge, then look at this blue edge and this blue edge. You have this blue edge, one missing edge between this and another missing edge like that, right? That means that this and this would have been adjacent in the auxiliary graph, and I wouldn't have given them the same color, right? Blue. So this is an edge, right? And if this is an edge, what is its color? You look at this, this edge, and now you look at this edge. So they form a C4, right? So I would never have given it the color blue, right? That would be a red edge, right? So similarly, the same argument can be said on top. It's symmetric, right? So that is a red edge, right? So now we have the same situation like this, right? But it goes one more step. So you repeat the same arguments, you get that these are blue edges. Again, you have another situation like this, bad configuration. You repeat one more step and you get that. Okay. But then what does this tell you? Now it says that you have a bad configuration of type 1 on A, X, Y, and D, right? you have another bad configuration. But this is lexicographically smaller than this. Oh, okay. So maybe I forgot to say something. So you start with the lexicographically smallest thing. Okay. Okay. So I want to first prove that this kind of a thing won't be produced by the algorithm. So I should have said in the beginning that suppose it is produced, then take the lexicographically smallest such set. Okay. Sorry that you have to take so out of all such problems in the coloring that you generated, you take the set which is lexicographically smallest, okay, and then you do the same argument, and then you can finally find that okay, there is another set that is even smaller lexicographically, right? Because this xy is smaller than bc, and this a and d occur in both the sets, so this is smaller. So that is your contradiction. So this won't happen, right? So this kind of the lexicographically smallest bad configuration cannot be of this form, cannot have a single red and two blues. But what if your lexicographically smallest configuration of type 1 has a blue here and two reds, right? Then we need some more case analysis, but before that, but that's also not hard. So if this was the case, then first thing we can show is that this can't happen. In your Lex BFS ordering that you started out with, you can't have D less than A less than C, because if that was the case, right, notice that DC is an edge, right, but DA is not an edge, right? Then the Lex BFS property tells me that there's an X that is even smaller than D, such that this X is adjacent to A and non-adjacent to C, right? So there is this X that's adjacent to A and non-adjacent to C. So this must exist. If your Lex BFS ordering orders these vertices as D, A, C, then there must exist a vertex X which has these two properties, right? But if this is the case, then what can you say about this edge? What will be its color? It will be blue, because it forms an, it is crossing with this edge. So my coloring is, so they will be in the same component of my G prime. So inside one component, my coloring is always valid, right? So that is blue. And if that is blue, then you can find that this XABC is another configuration of type 1, right? And this XABC is smaller than ABCD, right? Because this X beats D, A and C, right? And B is present in both the things, right? So X is something that's smaller than D, A and C, so it will help this guy in beating D, A and C, and B is not going to help because B is present here also, right? So that means that DAC is not possible. So in the same way, symmetrically, you can show that ADB is also not possible, okay? So let me just write both of this here. So these are not possible, okay? So I'm almost, okay, so I don't think I'll have time, but it's a simple proof, believe me, it's not hard. You just have to, there will be an inductive argument here which will give you these edges. That's it. Okay, it's just inducting. The proof is not this thing. You will get this, and finally, the only thing that matters here is that there is this edge UV which is lexicographically smaller than CD. This is the guy which implied CD is the red color, and there will be one XY which implied this edge AB. So this is the smallest guy in its component. This is the smallest guy in this CD's component. And then you get that this YXCZ, right? Because of this missing edge, it is a bad configuration of type 1. And this VUBW is another bad configuration of type 1. Okay, and you have these things, lexicographic this thing, and then it's just using these things. It's just this two-step thing. You can show that there's always something that is smaller than ABCD.
So this is where you use the ordering.
This is the only place that we use the Lex BFS ordering. We haven't been able to get rid of the fact that we need the Lex BFS ordering. We don't have any graph that with a bad ordering. Okay, so far. But the proof is very simple if you have the Lex BFS ordering. So that gives you the contradiction, which tells you that there are no type 1 violations in your coloring, right? Now the type 2 violation is a simple thing. So suppose that you have no type 1 violations, then you also won't have any type 2 violations. because it's just that because it's got the color blue and not two colors, it's not a bicolored but a single color blue. There's always exists something in its component which will be red, and this has to be an edge, because if this was a missing edge, you'll have two red edges with two missing edges. Now if you color it blue, you have this configuration of type 1. If you color it with red, you have this configuration of type 1. So that's it. That completes the proof. Oh, thank you.